Hello, 5th and 6th grade. This is your video for science for Tuesday, March 23rd, and we are starting a new section on light energy. And so we're looking forward to this of your the beginning of your three last chapters that we have in this. And so we are going to go ahead and get started here, and we're going to be reading about light energy. Now you have two work text pages to do, pages 160 and 161. 159 was done yesterday, and so 159 would have been the first part here. Now let's look at those really quickly, and let's see what we are looking at for doing today. So in that first one, 160, you see that it talks about different types of waves. You have light waves and sound waves, and it asks you to identify the characteristics of the difference between the two, and there are differences between the two for sure. And so we're looking forward to getting this done. And then you have a study guide on page 161. 162, you're going to be doing basically a sort of a puzzle thing, but that's not until tomorrow. And so let's go ahead and look at then what we're reading today, and starting with page number 238. And on page 238 it says this: the people who first discovered X-rays many years before World War I were surprised and amazed by what these mysterious rays could do. It was as if they were a kind of invisible light that could shine right through solid objects. X-rays share many of the same characteristics with light that you can see. Characteristics of light. Light is a form of wave energy. It is constantly moving throughout the universe. A light ray travels in a straight line, but the matter around it moves up and down. Light waves spread out as they move away from their source like ripples of water. Ripples of water move away from the place a pebble is dropped. However, light travels much faster than water. If you could travel at the speed of light, you'd be able to go around the world about 7.5 times in just 1 second. Though light waves carry energy just as other waves do, light waves are different from many other kinds of waves. The energy of water waves and sound waves must move through matter. Light waves, though, can move through both matter and empty space. Because light waves can travel through space, light from the sun and other stars can reach the earth. Light waves also move faster than other types of waves, such as sound. Light can travel through space at about 300,000 kilometers per second, or 186,000 miles per second. The sun is about 150 million kilometers, or 93 million miles away from the Earth. Yet light from the sun reaches the Earth in about 8 minutes. Scientists do not know of anything that can travel faster than light does. Look at the bottom there. It says history and science, or science and history. One of the first scientists who tried to measure the speed of light was Galileo. In the 1600s, Galileo and his assistant stood on top of two hills that were about a mile apart. Each of them had a shuttered lantern. Galileo flashed his lantern. As soon as the assistant saw Galileo's light, he flashed his own lantern. Galileo tried to time how long it took before he saw the answering flash of light. Since light traveled so fast, Galileo was not able to measure the speed. More than 200 years later, another scientist, Albert Michelson, was able to make an accurate measurement of the speed of light. He used a special 8-sided revolving mirror on top of a mountain in California. On to the next page. Comparing waves. And this will be similar to for the section on page 160 at the top there. Sometimes scientists classify waves by whether or not they can move through empty space. Waves that can move through space are called electromagnetic waves. Light is an electromagnetic wave. Waves that can move only through matter, such as sound waves, are called mechanical waves. Scientists also classify waves by the direction in which they move. Sound waves move in the same direction as the matter is vibrating. Waves that travel this way are called longitudinal waves. Light waves move differently. If you make a wave with a rope, you can see the wave traveling from one end of the rope to the other. As the wave travels forward, the rope moves up and down. The direction that the wave travels is perpendicular to the up and down movement of the rope. This is an example of a transverse wave. Waves that move perpendicular to the wave or that the matter is moving are called transverse waves. Light waves are an example of transverse waves. Right? And then on the next page there, on page number 200. Page 240, properties of waves. There are many different kinds of waves. Some are tall, others are short. Some move quickly, but others move slowly. All waves, though, have the same basic properties or characteristics. These properties include wavelength, amplitude, frequency, and speed. Transverse waves look like a series of hills and valleys. The top part of the hill is called the crest. This is the highest point of a wave. The trough is the lowest point or valley of a wave. Scientists use the crests and troughs of a transverse wave to measure the length of that wave. Its wavelength is the distance between two crests or between two troughs. Waves with short wavelengths have more energy than waves with long wavelengths. Another property of a wave is its amplitude. Amplitude is the height of the wave, or of a wave. If you stretch a rope tightly, it will be in a straight line. Think of this straight line as the rest position of a wave. Moving one end of the rope will make the rope vibrate up and down. Part of the rope will move above the rest position and make the crests of the waves. The rope will also move below the rest position, forming the troughs of the waves. The distance that the rope moves above or below the rest position is the amplitude or height of the wave. Amplitude is your secret word. Page 241. And so you see there at the top there you have a couple of the wave frequency, which is how many within a certain time period, which is 1 second. And you have the direction of the waves, and you see where it's going, and so you see the frequency of 7 at the top one, 9 at the bottom one. As the rope moves up and down, many waves move through it. Each wave has a crest and a trough. You can count the waves passing a point by counting either the crests or their troughs. The number of waves that pass a certain point in 1 second is the frequency of that wave. A wave's frequency is not the same as its speed. Frequency refers to how many waves pass by a point in 1 second. Speed refers to the distance that one wave travels in 1 second. All waves have specific speeds, frequencies, amplitudes, and wavelengths. And so in the science and math there at the bottom, it says the speed, wavelength, and frequency of a wave are related mathematically. If you know the wavelength and frequency of a wave, you can calculate its speed. Suppose a wave had a wavelength of 6 centimeters and a frequency of 5 waves per second. The wave of the speed would be 30 centimeters per second. Wavelength times frequency equals speed. All right, and so the wavelength, the distance between the trough or the height of the wave, and times the times the frequency is going to equal the speed of the wave. All right, that's it for science for today. Have a wonderful day. We'll see you tomorrow. Bye.